In this video, we'll finish up our discussion of section 7.1, the definition of a Laplace transform. We're going to go ahead and put the rules together using that they are linear, that the Laplace transform has linear properties, and then we're going to take a look at a piecewise function. Okay, so how we're going to break this down, we're not going to have to go through the definition at all, which is great, and you guys are probably like, thanks. All right, so Laplace transform, we're going to split it like this. 3 times that, and then I can also split minus signs and plus signs. So this is actually minus 2 times the plus of 1. Right? So we can break down almost anything like that as long as it's linear. We're going to run into issues in a little bit. All right, so we get 3 times, remember that t was 1 over s squared, minus 2 times, and then 1 was 1 over s. That's a fine answer, but we are eventually going to have to put things together because we're going to have to flip things around, put things together, and take it backwards. So if I were to get a common denominator here, which is s squared, I'd get a 3 from that fraction and a minus 2s from that fraction. That would be a great answer for that. We'll eventually work on going backwards. All right, so the next one, we can write this like Laplace, take out the negative 2 times the Laplace of e to the 5t. Minus, and then we'll go ahead and do Laplace of cosine 6t. Okay, so we just got to follow those rules. This is going to be negative 2. And remember, the Laplace transform of an e function is just 1 over whatever the k is. You do s minus whatever the k is. So minus 5 here. Minus, and then we know that cosine has the s on top. Sine had the k on top. And then we do s squared plus k squared, which is 36, or 6 squared. We don't need to put those together. Eventually we will. And if you want to practice now, the back of the book probably puts it together. It's not going to get much cleaner because those have no factors in common, the two denominators. So we'll just leave it there. Okay, so you will have to work if you're not strong on like adding fractions that are rationals like this. You should probably look up addition of rational expressions and go ahead and remind yourself. We're going to do quite a bit of that. This would be the week to catch up on stuff like that because we're doing one section per week. So put the work in for each one of these, each example, and maybe do a few more. All right, so the last one here, we have 1/3 times the Laplace of e to the negative t plus the Laplace of t minus 9 times the Laplace of 1. All right, so we solve each one of these. Okay, so that 3 down there, how I deal with this is we're going to do 1 over 3 like that. And then remember, e to the kt is just s minus what's there, so that means this is a plus. It's just the opposite. T is 1 over s squared. And then the last thing is 9, and it's going to be over s. All right, I would work maybe I guess we could do it. It's not too bad. Let's do a common denominator. It's going to be, the common denominator will be 3 s squared times s plus 1. That's the whole denominator. We are missing an s squared from that one, times 1. From this one, we're missing a 3 times s plus 1. And then the last thing, we're just missing an s and an s plus 1. So there's our common denominator. I don't think anything's really going to clean up. So if we did this, I'm going to get a minus 9s squared over here. So I'm going to get minus 8s squared. I'm going to get a 3s and a minus 9s. So that's a minus 6s. And then I'm just going to get a plus 3. Yeah, nothing got simpler for us. So we'll just leave it alone like that. We could have probably stopped 2 steps above. So we will be messing around, like I said, with this like algebraic stuff, putting things together, tearing things apart. So if you're not great at that, please go review. Maybe email me. I can send you maybe a PDF I find online for practice or videos or something that could help you out. All right, we have one more example for this section. It's not too long, but it's very important. You're not going to be able to do the next 3 sections if you can't do this section. So that's why I'm giving you a whole week. That's why we let up. We did some heavy work in the middle of the semester to make this last unit not so overwhelming, to give you some breathing room and score well on your final. All right. The integral that defines our Laplace transform, since it was improper, which means that the limit as we approach infinity, it doesn't have to converge, right? We could have these Laplace transforms that do not converge. They actually give us a few examples. 1 over t does not have a Laplace transform. A Laplace transform. E to the t squared does have a Laplace transform either. So we actually have sufficient conditions that have to guarantee it. The function in question must be piecewise continuous. And they give us a definition next, and it must be of exponential order. T is greater than capital T. All right, so recall, and you may not know this, and that's okay. Piecewise continuous, what that looks like is if I have a finite number, finite means not infinite, number of points of discontinuity. So what we're like talking about for something like this could be like a step function, right? And it could go from one to another interval, even though our discontinuities, that thing is piecewise continuous because each section there is continuous and it's only a finite number of jumps between that in that interval that I created. Now the exponential order, hopefully I updated your notes before I do that, but if not, go ahead and fix that. I think I'm going to remember. Okay, f is an exponential order. And we have all these to be true, the capital T greater than 0, m greater than 0, and c is just some constant. If you can take the absolute value of your function in question and you can bound it by some capital letter with some e function where c is any number, could be whatever you want, and you can say your function is always under that for some t bigger than capital T. So it doesn't have to be there all the time. It's just at a certain t, big T, then would be above below it. Sorry for my dog barking. These are the sufficient conditions for Laplace transform to exist. So this allows us to do piecewise functions. And these are actually, they look like they're going to be horrible. And most of the time, they work out pretty nice. So this is how they work. If I take the Laplace transform of f of t that we have right there, then I need to take the integral from 0 up to your transition point of your function. And it says to use before your transition point 0 to 2, they say to use 4. So it's going to be 4 times negative st dt. And then plus, it's got to start at 2, go to infinity. And then this one works out really nice. The function in question here was times 0 times e to the negative st dt. So this whole integral back here is just going to go away. Now, if it were flipped, we'd have to put a number there, and then it just becomes a problem that we've been doing. It's really not anything difficult. The big thing here would be that we split wherever this transition point is that's how we split our integral. So that means our answer here is just the integral from 0 to 2 of 4 times e to the negative st dt. We've done that integral quite a bit now. This is going to be 4 over s, but a negative e to the negative st, and it's ran from, and I like to put my t's here because I'll forget, 0 to 2, right? The way I think about that is in my head, I'm just imagining the derivative. That's what I'm doing every time. All right, so I get negative 4 over s e to the negative 2s. And then if I plug in 0 and I'm subtracting this, I get 4 over s, and it's going to be e to the 0. So we just get that. Now, one thing to point out, and you should go back and look at all these answers. And remember, we took this function, right? We took the Laplace transform, and now it looks like this in notation. Now it's a capital F in terms of s. So here's a cool little thing that we'll end with. If f is a piecewise continuous and of exponential order, then the Laplace transform will always go to 0 as s goes to infinity. If you go back and look, we had a bunch of s's in denominators all the time. That is expected. All right, so that is one thing we know. If we get an answer that's not going to go to 0 as s goes to infinity, you messed up. Okay, so given that these two conditions are true. Now, there might be Laplace transforms outside of that. I am going by the theories given here, and we'll leave it there. All right, so this is our first section. Get a lot of practice in this. It is extremely important for the next 3. The better this foundation is out of this section, the easier the sections following will be.